So my name is Christine Broadbridge. I'm the Education Director of CRISP, which is the Center for Research on Interface Structures and Phenomena. So what is that? It's a materials research center. So what you're going to learn about today is a very interdisciplinary field that's part of material science. But what you'll find is material science is involved many different types of science and engineering aspects. And so that's something that you're going to learn about. You're in for a real treat. We actually have, back by popular demand, Dr. Corey O'Hearn. So we actually did this lecture last semester, and what ended up happening was it was the same day as Hillary Clinton was actually in town. So I think that if we had done that today, you probably wouldn't have had to worry about it, right? You would have beat her out, definitely. So what Corey is going to do today is he's going to talk about the mysteries of sand. So Dr. O'Hearn is an associate professor in the departments of, I have to read this out because there's so many things that he does: mechanical engineering and material science, applied physics, physics, as well as the graduate program in computational biology and bioinformatics, which is a really exciting field. Those of you out there who are thinking about different fields that are growing, all of these fields are growing, but I think bioinformatics is one that's particularly exciting to me. Before joining the faculty at Yale, Dr. O'Hearn was a postdoctoral fellow at UPenn in physics. He did computational studies of jamming transitions in frictionless granular materials and glass transitions in model glass-forming liquids. Okay, so you're going to know more about what that is after this demonstration and lecture today. Dr. O'Hearn received his PhD in physics from the University of Pennsylvania in 1999. He'll probably tell you a little bit more about the type of research that he's done. He did his undergraduate degree at Duke University and graduated in 1994 with a BS in physics. You see, with a physics degree, how much he has done throughout his career. He's an excellent teacher as well as a mentor to many students. So with that, I'm going to thank Dr. O'Hearn and let him take the floor. So again, you're in for a real treat. Thank you.
Can you hear me? Before I go on, I have to introduce my second-hand man. This is Thibault Bertrand, Dr. Thibault Bertrand. He graduated in May with a PhD in mechanical engineering and material science. And he's going to be helping out sort of 50-50 with all of the demos and talk today. So yes, so I'm Corey O'Hearn, and I'm going to be talking about the mysteries of sand. And so let's talk more about that. So sand is a part of a more general class of materials called granular materials. And what does granular mean? It means made up of small grains. If you think about it, actually everything is made up of smaller grains. Your body is made up of cells that's smaller than you. The chair you're sitting on is made up of atoms. But there's a key distinction. So up here I have water. That's not a granular material. The components in water are little water molecules, and they're very small. A nanometer is the relevant length scale there. Whereas here I have sort of garden variety sand, and the components of sand are these little sand grains, and they're not a nanometer. They're more like a millimeter or a centimeter. And that size distinction makes a world of difference in that we're going to be talking about granular materials like sand where the components are things you can see. So here are little particles, but they're not sand. They're the size of a micron. So that's if you look at a flower and you look at pollen. Don't look at the aggregate of pollen. Look at just a single pollen grain. Pollen grains are about a micron big. And when things are that small, they move without any other forces. They're not moving because you're making them move. They're moving just because of temperature. And so here I show you a picture of small grains. They're not moving because I'm pushing on them. They're just moving because they're small. These are called thermal fluctuations. And so anything above this size, anything above a few microns, basically anything you can see with your naked eye, are granular materials, and they don't move unless you push them. So we're now going to play a little game. I told you what a granular material was. I told you what wasn't a granular material. And you have to tell me if the pictures I show you are pictures of granular materials. This is going to be the next game show on TV. Is this a granular material? What is this? What is it? You don't have to be quiet. You have to be as loud as possible. What? It's salt. Is it a granular material? Yes, because the grains you can see. You can see the important grains of this material. What's this? Glass. Is this a granular material? Why?
Because there's no grain.
Well, there are grains, there are atoms, but you can't see them. Okay? So, for example, glass is made of silicon dioxide molecules, and you can't see them. The next one I think you're really going to like. This is my favorite cereal. Is this a granular material? Yes, it's Fruit Loops. You can see those Fruit Loops. What's this? Smoke. So this is not a granular material. The smoke is made up of air and other, nasty chemicals. It's not a granular material. Okay, so that set of slides, that was really fun. What you see from those slides are, what a granular material is and what it's not. They're all around you. So look at some of these pictures and see if you recognize any granular materials. I really like candy, so I immediately see the M&Ms. I see some rotini. I see my ibuprofen that I take all the time. I see coffee beans. I see rice. Granular materials are all over. And so we need to understand the fundamental aspects of storing, moving, handling granular materials. And because they're made up of macroscopic objects that you can see, it causes a world of problems, but also interesting phenomena. And we have 7 or 8 demonstrations which are going to illustrate these points. First, I'm going to try to motivate those demonstrations. So the first is, here I'm pouring water. Water conforms to the container it's in. Water is a liquid, and you can see when I pour it out of this vase, what is that called? Whatever. I'm pouring it, and it's flowing, it's not stopping, and then it goes into the other container and conforms to that container. So this liquid, this water, is not a granular material. But this is kind of confusing. Here we have an hourglass. Hourglass is, you can put sand in an hourglass. But the problem is that this granular material is possessing both solid features and liquid features at the same time. Where's the liquid feature?
The liquid feature is it can form into multiple areas.
Yes. Let me translate that. So it's sort of solid at the top, but then when it goes through this orifice, through this hole, it's flowing like a liquid. I can prove that it's now the thing that's confusing about it being sort of solid at the top and solid at the bottom is that a liquid can do that. A liquid will conform to the container it's in, but then it'll pour, and it's not in that shape anymore. But what you see at the bottom of this hourglass is it's forming a cone. A conventional liquid does not form a cone. It would just form a flat layer. So the fact that this is forming a cone is proving that this granular material is acting like a solid. It's not just avalanching and falling, forming a flat face. Remind me when I'm done with this section. Okay, so here's another example. One of my students really likes Starbucks coffee, and so wanted to carry out a demonstration of when the system is behaving, when a granular material is behaving like a liquid or a solid. And so try to figure out when it's behaving like a liquid and a solid. So here you see it's intermittently behaving like a liquid and a solid. When it's flowing through the container, it's behaving like a liquid. When it gets jammed and stuck, when it forms this jam, it's behaving like a solid. And so this is both interesting and cause a great consternation. What if I wanted to flow granular materials through some tube? I would never be able to predict when it would get stuck or when it wouldn't.
So now we can play a little game with that.
Okay.
We have actually examples here of little granular materials that we packed up in those bottles, just like the video that you just saw. And we're going to see if they flow or not. And that's actually a whole field of research. There's people at UPenn where Corey did his PhD that are studying that every day, just studying how granular materials jam in those constrictions, basically called hopper flows. Here I have this blue bottle with a pretty large opening on top and little star-shaped plastic beads in them. I have another bottle with glass pebbles. I have a bottle with a smaller opening with little wooden beads in them. A non-connectors bottle with coffee beans in it. And I have this same blue bottle with little glass beads. Those are very, very small. You can see them here. The question I'm going to ask is, do you think they're going to flow? Do you think they're going to jam? So let's start, for example, with this little glass beads. They are 500 microns, about a millimeter in diameter, and they are in a pretty big opening. If I just start pouring it, will it just flow or will it stop? Flow? Let's just do it. Okay, I never got to jam this one.
Okay, so one important variable that you have to consider is the ratio between the particle that's inside and the hole it's flowing through. And think about what that ratio has to be for it to get stuck. Does it have to be 1? It doesn't have to be 1. In fact, 5. Good guess. So let's think about it. I mean, let's do it. Let's prove it.
So now I have coffee beans in this bottle. What about those coffee beans? Any idea?
Yeah.
I would say the ratio in between the size of the coffee bean right here, I don't know, half a centimeter, and the bottle opening is 1:4. Any idea? Is it going to flow or not? Flow? Yeah, it kind of slowed down, but it never really stopped. So that one is flowing. What about now these little wooden beads? There's variety of sizes in there, but they're all about a centimeter, and the opening is about 2, so it's 1 to 2. Is that going to flow or is that going to stop? It's somewhere in the middle. And you're saying 3, but what could it depend on? Right now, all that we've done, coffee beans are pretty spherical, like beads. The little glass beads were very spherical. These were also very spherical. What could it depend on? What could this ratio depend on? You're saying 3. That may be true for these spheres, but maybe it's not true for these little star-shaped particles. Maybe it's not true for those glass pebbles, because their shape is completely different. So there's a lot of things that can go into that. There's shape of the particles, and that's always the case in granular materials, and we'll show you in a second. But shape goes into balance. Friction in between the particles goes too in the balance. And we're going to be talking about that in a second. Next one, those pebbles. The pretty big blue jar. Stop or flow? Stop. This one just flew. What about those?
Let me make one comment, is that it's interesting that one flowed, because if you take one of the dimensions of those discs was fairly big, and it was comparable to the opening size, but they completely flowed out. So shape is plays a very important role.
The last one are these little star-shaped particles. Are they going to stop or are they going to flow? Stop? You always say stop. These ones just stopped. I can tap them a bit, and you get them to flow. The study of is it going to flow, is it going to jam, is it going to stop, is an actual industrial problem. Think about your production line when you're in a pharmaceutical company, and you have all these pills flowing down, or even your M&Ms, your candy company, and you've got all those M&Ms flowing down. How can you control in all those production chain the fact that it's going to stop, it's going to jam, it's going to stop flowing, or it flows to get in your package and get to the consumer? That whole problem costs actually a lot of money, and that's a problem that's under research right now.
Okay, just to further motivate that, so we talked about these hopper tests. We're going to show you a little more in a little while, which tells you when is the system behaving like a liquid or a solid. Here's another example that granular materials can behave like solids. Here, this is an intricate sandcastle that's being formed. The reason why this can be formed is that it's wet. We're going to talk about that in a little while. But it can form these very 90-degree angles, which is amazing.
Little trivia question. Does anybody know what's the tallest sandcastle that's ever been made? Like the world record tallest sandcastle? Any idea? Guesses?
10 feet.
Tell me. 15 feet. Do we have better? 20 feet. 30 feet? 35? Well, it's actually about 14 yards. So it's actually 55 feet or something like this.
More.
50 feet, something. 14 yards. So imagine about, I would say about twice the height of this room, maybe a little less. That's the tallest sandcastle that's ever been recorded. So those granular materials in the proper conditions can act as solids. They can be self-standing. They can support some sort of weight and some sort of load.
Okay, so the next thing we're going to talk about, trying to understand whether particular granular materials are behaving like solids or liquids, is what's called a slump test. So try to remember that. You can impress your engineering friends. This is often used in the concrete industry to determine how well the concrete is performing. But what we're going to do is we're going to pour out different granular materials and see what type of conical shape that the granular material forms as it is poured. And so we can measure the average angle of the cone. So it's basically the angle that the cone is making with either the vertical or the horizontal surface. So if this angle, if you're measuring it from the vertical, is 90 degrees, then it's a liquid. It'll be a flat surface. And so we're gonna study that. The other thing is the less steep this conical angle is, the further that the material will flow. So there are two measurements that you can make with these slump tests. You can measure what's called the angle of repose, which is what this cone angle, but you can also measure how far the run out is after the slump test. Okay, so we're going to do 4 slump tests now.
So we're going to do slump tests here with different materials, and as there's here, what we're telling you, and I told you a second ago, is the angle of repose has a lot of stability quantities in granular materials. What tells you if it's a solid or a liquid depends on the shape of the particles, depends on the friction, depends on the density, depends on the size of the particles. So here I have completely different granular materials. The first one is just regular long grain rice. Okay. The second one is going to be our favorite coffee beans we already used. And then I have 2 types of sands. I have a red sand and I have a white sand. Other than the color, the main difference in between these 2 guys is that one of them, namely the white sand, is a little coarser, a little bigger. The white sand is very, very fine. I can actually pass that around if you just want to have a look at them.
This is going to be very important in a few minutes in another demonstration.
So we're going to be playing another game here, and I'm going to ask you, what do you think flows best? The very fine red sand, the slightly coarser white sand, the coffee, the rice? What's going to form a pile that has the biggest extension? And I'm going to do it on these pieces of paper right here, so I can mark out after we did the slump test with a Sharpie, and we're going to have a look at them. So keep that in mind, but I'm going to take a couple answers. What do you guys think? Rice is going to flow the best, the least, the most. Okay. So rice number 1. Does everybody agree? No? The red sand is going to flow the most. Okay. So we've got here rice. Someone else thinks red sand. Right here. Do we have a no? Anybody else? Basically, someone is going to tell me coffee, and the other one is going to tell me white sand, right? So for now, we have no idea. So let's have a look. But let's keep in mind that we basically have someone who told us rice, which is a big grain. It's also elongated. It's pretty smooth. It's not very frictional. Someone who told us red sand, which is very, very fine grain. It's a powder, and it's also very coarse. There is lots of friction in between the grains. So I'm going to do them one by one, and we're going to start with, let's start with the white sand. I'm just going to pull the cup. It's going to form a pile, and we're going to look at how big it is. Okay. Where is the sharp? Right here. So it makes a pretty nice pile. It's actually a nice conical shape, just like you saw on the slide, and just like there was in the hourglass. And I'm just going to mark up the size right here. It's about that big. I'm going to do the rice now. Not bad. Not bad, pretty similar. A little bigger maybe. The red sand. The red sand was, I'm sorry, not a good answer. The red sand is actually, for now, you're going to see in a second, it's the smallest of the piles. It's the list extended. And the last one we have is coffee beans. Okay? I don't see it on the board.
So those roll better.
Yeah, exactly. So if I take really the extent, this is coffee beans. Okay, let's just get rid of the material. I'm just going to put them up on the board and we're going to compare the sizes. Can you help me with that?
You should draw a smiley face on it.
Thank you for holding the card. What do you say?
You're going to separate them later.
Yes, we are. We're recycling all that. Grain by grain. Okay, so if you look at what's now on the board, can everybody see properly? Basically what we are saying is that the best flour is the coffee beans. That's far in front of the other. Comes next, I would say,
Rice.
probably the rice.
White and then red.
The white sand. And the red sand. And this difference in angle repulsion between the white sand and the red sand is very important. Because this difference in angle repulsion is, as I was telling you, coming from the size of the particle, the friction between the particles, and so on. But it's actually creating other problems that you see all the time in industry when you have mixed powders of different sizes. The problem that we're going to see is called segregation. So here I have an hourglass that I basically filled up with the red, a mixture of the red and the white sand. Okay, and I'm shaking it. It's very well mixed. There is no problem. Do you see any structure in it? It's completely mixed. Okay, you can shake it a little more. Right here. And now I'm just going to tip it and I'm going to let it go. And we're going to see it just flowing. Can you start seeing something?
Okay, if you start seeing something, let us know what it is.
The top and the center, you're saying you can see that?
Yes?
Uh-huh. Uh-huh. Can you see something at the bottom? Those of you who are in front, what do you see?
Every once in a while, the top of the sand tower is going up
by like a couple centimeters.
Yeah, that's true. And the reason why it's doing exactly what you're saying and also switches from the left to the right a little bit is because it's reaching the sides. So when it's reaching the sides, it cannot flow more on one side. So that is going to be piling up, leaving some space on the left, so it's going to come and fill up the left, and then the right, and then the left. So it actually fills it up layers by layers. But is there anything else you can see here? I'm trying not to move it too much. It's completely layered. I started from a completely mixed distributions of those particles, and just going through an hourglass, and just because the angles of repose of the two materials are slightly different, ever so slightly, a couple centimeters, you actually have nice layers, nice stripes here. I can just go around for you to see it a little better. Do you want to take it? Sure. Try not to shake it too much, you're going to mix it.
So can anyone think of a problem that this would cause if you're processing granular materials? Oh, yeah. So one thing that can happen is in the pharmaceutical industry, if you're making a pill and the medication powder has different properties than the filler of the pill, then maybe some pills won't get any medicine. So you want, in many situations, you want mixing systems to remain mixed. In this system, what happens in hopper flows is if there's any difference in the materials will segregate into a material that's all similar and another material which is similar.
Okay, so now we've been talking a lot about flowing and granular material as a liquid. We haven't talked much about granular material as a solid and what's actually holding it together. I mean, you guys, it's October. You've been this summer maybe to the beach, West Haven Beach, or Hammonasset nearby. You can walk on the beach. You can walk on the sand. You're not going to fall through. It's not a liquid. When you go in water, you can't walk on water. So, what do you say? There is a problem with quicksand, but that's a slightly different problem. On normal sand at the beach, if you go to Hammonasset, you probably won't find quicksand. You can walk. You can walk on top of a dune and not fall through. What's holding your weight? What are the forces at stake in granular materials that make those pile a solid? We took away all those slump tests that we did. If I had let them until the end of the demonstration, they would still be here. They are not flowing. They are completely stable. So now the question is, what makes a granular material not a liquid, and what makes it a solid? Corey, do you want to talk about forces?
No, let's do this one first.
Okay, first. So all those grains, all these piles are made of little grains that are all in contact. Okay, they're all touching each other, and at this contact, there is a repulsive force, meaning that I cannot push particles together without applying a force. And there's also friction, which means I cannot push them up and down without applying a force. Those two forces are critical in granular materials. And these forces in granular materials are actually not propagating the same way as they would in a normal elastic solid. If I were to take a little piece of rubber and push on it, all the forces would go down in the same direction I'm pushing. In a granular material, it's slightly different. They're propagating along those contacts in between all the grains. And I'm going to show you that in a second. What I have here is a 2D model granular material. That's my granular material right here. All these beads right here, all these little discs that you see, have been cut out of a material that's called photoelastic. Photo is for light, elastic for elastic. This material has the awesome property that the amount of light that goes through depends on the amount of stress or amount of force it's under. Okay? So in the experiment I'm going to show you, the more light you're going to see, the more forces or the more stresses there is in that particular grain. Okay? Is that clear? Now the problem is that, as you can see, there's nothing going through. All the light is going through. Well, there's a little trick to it. I'm going to have to put polarizers around it to actually see that manifestation. Polarizers are nothing else than what you have in your polarized sunglasses. Have you ever looked at the screen of your iPhone or the screen of your Samsung with polarized sunglasses? What you see are those iridescent colors. There's like rainbow. You can't really see your screen very well. Well, it's because polarized sunglasses are only letting the light go in a specific direction. So that's exactly what I'm going to do here. I'm going to be filtering the light in one direction by the first polarizer. I'm going to be refiltering it with the second polarizer. I'm just going to put big sunglasses on my experiment to be able to see what's going on inside. That's all. That's better. Okay, so you guys are starting to see something now. You're starting to see that there is little strikes in it, okay? Little parts that are darker, little parts that are lighter. Those are the forces in the system. It's exactly how the forces are propagating. Now I'm going to take a plunger and I'm going to push on the system. We're going to look together at what it looks like. Can everybody see? Am I on the way of anybody? Let me just go on the other side so you can see better. Everybody can see that? Okay. Can someone just describe what's inside? Are the forces propagating everywhere the same way? You. Yeah, that's just what I said before. That's perfect. It's basically the more forces in the material, the more light you're going to see. But do you see the same amount of light everywhere in every grain? No? No. That's what we call chain forces. In granular materials, there's something that's peculiar about this material that's not happening in liquids. It's not happening in a continuous media like an elastic solid. The forces are not propagating the same way everywhere. They're actually those chains that are reaching out from widely different parts of the material and providing the stability. And those chain forces are exactly what you see in this little experiment right here. So for instance, this chain of light that you can see right here is one of those chain forces, linking the top plunger with the side of the container. And that's what providing the stability in those materials. Okay? Now, not only those forces are kind of reaching from the boundaries to the plunger here, they're linking all the particles together in some complicated way, they're also frictional. They're not, if I were to take these two grains and push them next to each other, just slide them next to each other, there is a force that's associated to that. And that's exactly what Corey is going to show you now.
Okay, now we're gonna talk about force change, but we're going to talk about its consequences in a material. So right here, I have a dowel, a wooden dowel. In here I have sand, and here I have a glass beaker. So the glass is in the glass beaker, and I'm going to force the dowel into the sand. Kids, you need your parents' permission to do some of the things I'm going to do. Okay, so this is a common, so here's a demonstration. So what would be interesting is, originally the dowel was separate from the sand. There was no contacts, the dowel was outside. But then I shoved the dowel into the sand, and the dowel is making, the grains are making contacts with the dowel, and the force chains are connecting then the dowel, the sand, to the beaker side. There's all these force chains that you saw in that propagating, existing in this container. And if those force chains are really strong, if they're making strong connections between the grains, between the dowel and the container, I could pick up this dowel and everything would be picked up with it because these force chains are connecting everything. Do you think that this will work? Okay, we have some yeses, we have some nos. Okay, and it's all about what's the surface area of the dowel? Like, are there enough contacts on the surface? What are the size of the grains? Are they frictional? How heavy is the beaker? How heavy is the sand? So it depends on a lot of variables. Didn't work. Okay, I knew that wasn't going to work. Okay, now we have. Let's do this one first with me.
Cool. Do you trust me? Now is a moment.
What I'm going to do is I'm going to get on here, and he's going to hold that thing over me, and see if that works.
Do you have medical insurance? So
Just get it over with.
what am I doing now? What I'm doing is I'm literally just compacting the grains a little bit so that when it goes down, more forces, more contacts are made in between the dowel and the grains and through the grains to the outside. So I'm just compacting this a little bit to gain a bit of stability.
Uh,
I'm going to pass quickly here.
okay.
Come on, a second time.
Okay, but it gets better. We're going to have a little competition. So we have 2 of these. What we're going to do is we're going to pass them up and down the aisles. And what you have to do is make sure that this doesn't break. So this allows you to see what's going on, but also, to sort of feel the integrity of this. So what was the difference? Essentially nothing, but this is now not glass, it's just a 2-liter bottle, plastic. The sand is a little coarser, and the dowel has a greater thickness. And so we tuned the variables a little bit, and now they work. It's purely dry. It's just dry sand, it's not cement. We're going to talk about cement in a second, but these are just dry.
Okay, you're going to the left, I'm going to the right.
Yeah.
Careful, it's a little heavy, okay? So if you don't feel like you can carry it, just...
Pass it to whoever wants it.
And don't fight for it, because if you shake it, it's on the floor.
If it breaks, it's okay. We'll start over. But we'll just watch this for a little while.
Just one thing, careful not to shake it too much when you pass it to your neighbor. I'll explain, we'll show you in a second why. I can take it over if... Ah, here you go. This one is not going to go yet. Okay, where is the black one? The black sand? Okay. Could I get it back? Do you mind? We'll keep it up after the demo if you want to play with it a little
you can
bit.
try it out and see if you can pick it up. So we're going to move on to buoyancy.
So just one thing. We said this is held up with all those chain forces. Okay. This is very stable right now. But let me just tap on the side, and I'm going to break all those chain forces. If I tap on the side, I can just take it out. Okay. Buoyancy.
So,
Do you want to put the water a bit in the middle?
yeah. So we're just talking about the solid properties of granular materials, but they also have liquid-like properties. And so one thing that you all know about, especially if you're swimmers, is buoyancy. And so buoyancy is related, it's a force that causes things to move up in water. And it's proportional to the density difference between the object and the fluid you're in. So in the case of this water, it's going to be the density difference, how dense the structure is that you're putting in, and the density of water. Now, so let's try this. So if something's buoyant, it's going to float, and that means that there's a density difference between the water and the object. So this is a foamy golf ball. Is this thing going to float or not? Okay. There's a tricky one. These are beads, but they have a hole in it. Are these plastic beads, are they going to float or are they going to sink? Here are those disc-like rocks. Are they going to float or are they going to sink? Okay, so this is basically, you can use this experiment to measure the density of an object. We have a couple other, we have a ping pong ball, and this is now a real golf ball. It's going to sink. A ping pong ball, it's going to float, because the density of a ping pong ball is essentially the density of air. And that's about it. So the next thing you can do is ask, can you do an analogous experiment in a granular material? The first answer would be no. You're going to try this experiment and the object is just going to sit on the surface. Because when the granular material is not being agitated, is not being vibrated, it's acting like a solid. And so the density is very high. And so now we're going to do a buoyancy experiment, but we're going to agitate, we're going to vibrate the granular material, and it's going to act more like a fluid. And so we can measure the density of objects using granular materials.
So it's going to happen on the two screens on the left and the right. But before that, what I'm going to do is I'm going to use a ping pong ball for this experiment, and I'm also going to be using just one of those weights we use, those fishing weights, okay? They're lead, they're pretty heavy. Is this weight here heavier? Is it denser than the granular material that I have here or not? This is just glass beads that I have in there. Is it? Okay, so normal buoyancy experiment in a normal liquid, what should happen? This should sink at the bottom. This is a ping pong ball. As Corey was saying, it's about the density of air because the shell is very, very light. What should happen in this case? Should float. Okay, so now if I just put these two guys on my granular material, I'm just going to put them right here. Well, they don't seem to actually be doing much. The weight is not going to the bottom. The ping pong ball is on the top. That's where it should be. It should be floating, okay? Now what I'm going to do is I'm going to sink this ping pong ball in, okay? I'm going to keep this weight up. I'm going to put another couple weights and another ping pong ball that I'm going to sink in, okay? When I sink in this ping pong ball, what do you see? What's happening? They're not. They're at the bottom. They're not coming out. Do you see them coming up? In the water they would. In the grains they're not. Any idea why? The rock is staying on top, yes, and the ping pong ball is also staying under. The reason why, maybe up there, tell me? Yeah? It's because the grains aren't agitated. It's because there's all these chain forces we talked about. Those grains are frictional. They act like a solid. They are here and they're keeping the material as a solid, and they're keeping those ping pong balls stuck at the bottom. And while the ping pong ball would like to rise up because they're less dense, this force, this buoyancy force, is not enough to overcome the forces in between the grains. It's not enough to break those chain forces, okay? But we can help them a little bit. I just told you that it's stuck because all the grains are in contact. So what I'm going to do is I'm going to shake this thing. I'm going to shake it up with just a little, this is the equivalent of your speaker you have at home, nothing more. I'm just going to shake it pretty fast and pretty strongly to break those contacts. What's going to happen is that all those particles are going to come apart. I'm just going to break those contacts and reset them. And let's look at what's going to happen. Okay, and I'm going to stop it right here. What happened? Anyone, just speak up.
The golf ball came up, and the balls came up and I guess the speaker kind of broke the solid,
Mm-hmm.
kind of melted it.
Exactly. If you want, you can see melting. I literally, with this shaking, I just made a liquid out of a solid. So lozumnators were back like in the water case, and my ping pong ball raised up, and the heavy objects that were on top, those weights, those lead weights, just fell and sunk at the bottom. Now what you see is that one of them came up really fast because, you know, as I told you, chain forces are not exactly stable the same way everywhere, so that one just raised up because the material was probably more fragile around it. The other one did not. The other one is actually stuck in the middle. Well, I can tell you that right now, I stopped the shaking, the contacts were remade, the forces are reestablishing in the material, it's now a solid again. Which means that I can wait here forever, and we can see that in an hour when you're done with all your demos outside. This is going to stay here. The ball will not rise to the top unless I actively shake it, unless I make of this material a liquid again from the solid. Okay?
So what we were talking about for most of the previous time was dry granular materials. So when we were doing the dowel test, when we were doing this vibrating of the granular materials, the systems were dry. There are two ways in which granular materials can behave cohesively. And so a cohesive material you can actually pull apart and it'll resist. You can tell that this system is not behaving cohesively because I just pulled grains off the top and it didn't resist me at all. So dry granular systems are what's called non-cohesive. There are two ways to add cohesions. Well, there are more than two. We're going to talk about two. One way is to add a little bit of water, and I drew it schematically here. Here we have just a little bit of water, and this you know about when you make sandcastles. You add a little bit of water to the sand. If you add too much, it's not good. You make a slurry, and then the sandcastle falls apart. But you add just a little bit of water to form what are called liquid bridges between the grains, and they act cohesive. So the reason why that happens is because fundamentally, water has surface tension. Water molecules are sticky. And you can illustrate that with this experiment, which I hope will work. You can do this at home. You have a cup. You're going to put a little water in it, and then you're going to put a top. Cardboard is usually pretty good. If you use paper, paper's a little too flimsy. What you want to do is make contact between the water in the cup and the top of this surface, and then turn it over. And the cohesive force of the water, the surface tension of the water, will keep it up when I flip it over.
I bet it's not going to work.
And don't add too much water. Oh, you saw it there for a little while. I'll try one more time. It's now soggy, though. So does anyone want to go under this? And and if I push too hard, well, this one's pretty good.
This one's pretty good.
So that's surface tension. And so you can do something like slump test to sort of prove the cohesion as well. And so this is going to be a slump-like test with dry granular materials, wet granular materials where the water is 1% by volume, and where the water content is 5% by volume. And so what we want to ask is which one is more stable, which leads to different flow outs. And so he's going to flip that. So you've seen the dry one. That just forms this conical heap. And then we do, so that one's very cohesive. You basically keep the exact shape of the container. And then when you add a little more water, you have this like slurry-like behavior, and the water content is too much and it drains out. And so this is this cohesive behavior of wet granular materials. The next thing that we want to talk about that allows you to have cohesion is not from water, it's from grain shape. And so a great example of this is a bird's nest. A bird's nest, at least if it's made of twigs and elongated particles, stays together, typically without a lot of glue. And so we're going to show that in two ways. Here is a little picture. It's just you throw randomly little thin rods together. I think this aspect ratio is around 50?
85.
85, so it's really long. The aspect ratio means what's the ratio of the longest dimension of the object to the smallest dimension of the object. And this one, it's 80. What is the aspect ratio of a circle?
What's this?
1. Every dimension looks the same. What's the aspect ratio of a square? 1. Every...
You're going into trouble.
To a good approximation, they're all 1. But then you get these elongated rectangles. They can be very long. And so if you have this aspect ratio of 80, it's very cohesive. But it's not cohesion from water. It's cohesion from the fact that they're intertwining. And so we're going to do that right now, kind of a slump test.
So right here inside this tube, if everybody can see, I have little plexiglass rods. And these are about 35 times as long as they are wide, okay? So the aspect ratio, as Cora was saying, is 35. I just pour them randomly in the box. Nothing special, no special preparation, no tapping, nothing. Just pour them in the box. And I'm gonna remove the container as the slump test we've done before, and we're gonna see. If inside I had marbles, big marbles, aspect ratio 1, what would happen? The marbles will be all over the floor and would be picking them up for the next 2 hours. In this case, because of the entanglement of the grains, because they're all making crazy contacts, we're going to see that it provides stability to the pile.
Can you push on this one?
I can push on that one. So this pile right here, you see that some of them were loose. They were not making a lot of contact with the others, so they just kind of splattered around, scattered. But most of the piles stayed up, and the angle on the side is about 90 degrees. We have a collaborator who had one of these with slightly longer rods, basically hanging up from his ceiling in his lab for 2 months before it started falling apart. And it fell apart because there were a little too much wind and perturbation. But it's very stable structure. It's actually stable somewhat in compression, so I'm going to pull down. You'll see that it's going to go down a little bit, but after a while it's going to resist my weight. So right now it's basically resisting. I can't push more down without breaking the sticks. It's pretty stable and shear, so if I just push it around. And that's basically a very simple geometric physical explanation of why bird's nests are so stable. I'm pushing with like, I don't know, 5-10 pounds with my hand, and this thing is not going under. It's not compliant at all. Birds basically weigh nothing. And on a typical bird's nest, you could sit about 60, 70 birds before you're even breaking it. And those nests are made for 1, 2, and a couple kids. Nothing more than that. So this very simple geometric explanation, physical explanation, might be behind, just the stability of bird's nests. That's one of the examples.
Okay, so one final note. So we did a lot of experiments where we think we know the answers to the phenomena the interesting phenomena we see. But there are many more mysteries in sand and granular materials that are unsolved. And this is one of them. So the mystery is that sound. It's called booming sand dunes, singing sand dunes. Mm-hmm. And so this has been observed in the Sahara Desert, in the Mojave Desert in California. But the wind is picking up the grains and then depositing them, and there's this sound that comes out, and we don't really understand what's causing it.
If you were in one of these dunes, in one of these places, there's about 30 places in the world where you can find those. And in the US, I've put some examples. So in Nevada, in Indiana, and California. So it's not completely remote part of the world. It's not just in Sahara. If you were to be on one of these dunes and you're walking around, every time you walk, you get a squeaky sound. Not like my mic, but a real squeaky sound. When you avalanche the pile, when you're on the avalanche side of the dune, so a dune always has a flat side, a plateau, and on another side, an avalanche side, which is at that exact angle of repose we demonstrated. That's what gives dunes those characteristic shapes. When you're on that side and you're pushing the grains down, you will hear this exact low rumble, this low sound coming in. When you walk on the top, you'll hear this squeaky sound. It's pretty crazy. Closer, and I've never had a chance to go. I just discovered that this morning. Apparently, there is a singing beach, a singing dune in Manchester by the Sea in Massachusetts. So if you ever have a chance to go up there, try to check it out and try to check if it sings as well as the video we're showing you right now.
Okay, so that takes care of the talk and demonstrations today. If you want to come up and ask us questions or play with some of the demonstrations, feel free.